Hello everyone, welcome to my channel. So today we are going to do Leetcode daily challenge, Palindrome pairs. So basically in this question, we are given with a list of words, and this list of words, we are required to basically check that how many pairs of palindromes are being there. So here you can see that ABCD is there, and then DCBA is there, right? So when we combine these, so basically it becomes a palindrome. Means, so because of that only we are having this, and when we check for DCBA and ABCD, then again it becomes a palindrome pair, right? So that's why because of that we are having this. So that's the thing which we are required to check for all the words which are being given to us in this particular what we say, that vector or vector which is being given to us. So before starting, let us start with the reading of this question, then we'll check for the constraint and then examples. So given a list of unique words, so all the words here are unique, return all the pairs of distinct indices. So all the pairs of distinct indices we are required to return in the given list. So the concatenation of those two words, that is word of I plus word of J, is a palindrome. So that's the thing which we are required to return. So let us first check for the constraints. So constraints basically are given to us in such a manner, like length of the word could go to 5000. That is, if we go ahead with n square solution, so it will directly have the 10 raised to power 6, right? And even the length of that words, okay. Here the thing is that the number of words which is being given to us, that could be this much about, that could be till 10 raised to power 3, right? And if we do our n square solution, then our n square solution would reach to this much. And one more thing which we are required to consider for each is that the length of each word is 300, at max 300, right? So when we go ahead with comparing one word with other words, so it will let us to have the time complexity 10 to 2 plus 2, that is 10 raised to power 4, right? So overall, if we combine, if we are having more loops inside them, so somehow it will become 10 raised to power 6 plus 2, or might be 2 more. So it simply becomes a solution of 6, 7, 8, 9, 10, right? So this will definitely give us TLE. So that's why we are required to come out from that brute force solution to an optimized solution, where we get our answer in such a manner that we utilize the length of the words at maximum and the number of words to the minimum. Because here you can clearly see that this 10 raised to power 3 is greater than 10 raised to power 2, right? So that's why we are required to utilize this thing only, that we make a solution where 10 raised to power 2 is utilized. If we want to go ahead with a square solution, then in that sense 10 raised to power 2 is utilized more rather than 10 raised to power 3, so that it don't give us a TLE solution. So that gives us hint for this solution. But even of this hint, we very well know the way they have given to us, the first thing which comes to our mind is a brute force solution only, because here the first thing which we are required to check is that is it a palindrome or not. So for checking a palindrome, we already know that the solution would be order of n, right? And the second thing which they want us to check is to check pairs, right? So we will be checking for each word which is being there and comparing that each word with each other word, right? So in that scenario only, then our solution again becomes n square. So in all these sense, here n simply would be for n, basically it would be the number of palindromes which are being there, which we will be passing into the length. Basically it would be something like this. So that's why the overall time complexity somehow becomes n cube into L, or in some scenarios it is n square into L. So because of this time complexity only, in the brute force solution we were getting TLE. Now, so let me first show you about the brute force solution, because if we don't know about the brute force solution, then it becomes much difficult for us to come up with the optimized solution. So here is my brute force solution. So the thing what I was doing was, I was simply going ahead, means here is the answer because our return type is basically vector to vector int. So that's why we are taking like this. Now here I'm running a n square loop where I'm checking for each word for each pair, that is I with j, that is 0 with 1 and 1 with 0 also. So that's why we are starting from 0 for both. And then here we are basically concatenating both of I and j, and then we are passing that. First we are checking that if that I is not equal to j. This is for that scenario that the word itself doesn't go ahead and check for a palindrome, because if a word itself is passed, then it would be surely a palindrome. We all know about that. So that's why we are checking that if it is not equal to that index itself and its palindrome is true, then we will be pushing that pair. So this was the brute force solution. Here you can clearly see that this is n square solution, right? And then while we are going ahead with this palindrome thing, so here palindrome you can clearly see it will be up to the length of the string which is being with us, right? So that's why this whole solution becomes order of n square into the length of that word, that is this one. So this is how this solution becomes, and this is the fact that it was giving us TLE, because here you can clearly see that this solution comes out to be 3 and then 3 6, right, into the length that is 10 raised to power 2, so it becomes 10 raised to power 8. So when a particular solution exceeds the 10 raised to power 5 or 10 raised to power 6 limit, then it gives us TLE. So that's why it was giving us TLE. Now comes the part that how we are required to modify this particular solution. Here we were doing it clearly that we are just passing that particular word and then checking that it is a palindrome or not. Means after concatenation of those words it is a palindrome or not. But for overcoming with the TLE part and for using that length of the word rather than the number of the words as the most you can say most dominant factor in this solution, we can check for each length in such a manner, means checking for the prefix and the suffix of that particular word. So in that context, what we can come up with is that when we are checking for the prefix part and checking that if that prefix is palindrome or not, and or we are checking for the suffix of that word if it is a palindrome or not, then a particular portion, that is the middle portion, is only left, right? And that middle portion we can easily accommodate if we find such a word in the reverse order. So all this, by this thing only, we are able to come up with a solution in which we are using trie. So basically, even if we use a map or unordered map in this case, so you can clearly see that in unordered map or map, we have one property that the unique elements are basically eradicated in that sense, right? So because of that, only some test cases might miss. And taking care of that test cases only, the Leetcode has presented some more test cases where only a trie solution will work. And that's why even the unordered map or map solution were giving TLE. So now, let us go ahead with the trie solution where even the duplicate words are being kept and we can easily analyze. But the core factor for this is that we are using prefix and suffix matching so that we could come up with the palindrome even with the partial portions of that particular length. And in that trie solution also, the way we were taking care that that particular index is not the same about which we are finding. This also we are required to take care. And one more thing which that will add up in our trie solution that I'll let you know later. So let me explain you that how we can come up with a trie solution. So let me show you the explanation part for the same. Then I'll show you that how we are required to code it. So here is the part. So basically, in general, how we do a trie solution. We are having a root and then each alphabet is having their own words. So that's the thing is there in the trie. And how we are able to recognize that that particular word is ended. So for that particular factor, we always mark the end of that word as true, right? And or other I'll basically mark that false, right? That is the scenario. But in this case, we won't be doing like that. And the reason for that purpose is that see, if this SLL is there, right? Here you can see that there was one word also S, right? So S itself is a palindrome. right? So the thing is that when we add this S in this particular trie, right? So if it is marked as true, right? So the thing is then when it is marked as true, then in that particular scenario, when it will be checking for this particular node, then it will say that it is a palindrome and it will store what was in this. For this it was 3, right? So it will store in our answer as 3,3, which we don't want, right? So that purpose only we are basically taking the end of each word with the index of that word. So that's a scenario which we have tweaked in our trie. This is the first thing which we tweaked, and the second thing is we are storing our each word in the reverse order, so that when we traverse our given string, right? So in that particular scenario, we will be traversing in from front to back, right? But here we are storing from back to front. So we will be easily able to come up if the index of that word is not equal to the index of the given word, right? And if it is a complete match, then surely we figure out that it is a palindrome and we will store that. So that is the thing, and that's the reason we are storing every word in reverse order. So now let me say that storing words in trie in reverse order, and marking end of the word by its index, and if that word is palindrome, then the index is stored in the palindrome index. So basically our trie node is something like this, that in our trie node we are having index, we are having this palindromic index vector, means palindromic index vector is there, this is int and this is vector, this is one external thing which we are having, and for storing each word we are having a root which is basically of size 26. So these are the three things which make our trie node. Because for creating a particular trie, even in tree also, because the tree and trie, basically tree is a type, trie is basically a type of tree only. In tree, how we define a particular tree? Let us take a binary tree. So in binary tree, we all know that there is left and the right, right? So left node and right node are basically two pointers which are basically pointed towards the left side of the binary tree and the right side of the binary tree, right? So that's why we are having left node pointer, right node pointer, and the root node pointer in a binary tree. So like that only in a trie, the mandatory two things are, one is the index which marks the end of the word, and the other one is the root node. Basically this is that fact which will be storing all the words which are being there. And this is one extra thing which we have taken as per this particular question, that is vector of palindromic index, which will help us to come out of this particular solution more early and able to come up with all the test cases which are being there. So now let me start with that here it is now clear that how we are storing. First thing is that we are storing in reverse order. So at each character we are having -1, but when it comes to the end of the word, then we will be storing the index of that particular word. You can clearly see that here end of the word is 0, here it is 1, here it is 2, and here it is 4. But in each other there is -1. So this simply reflects that end of the word has not reached. Now comes the part, this was for the index and the root 26 which was there. Now let me explain you for this portion, means vector palindrome index. So now the thing is that checking for prefix and suffix matching to reduce time complexity for such cases. So for this purpose only we are storing indices in that particular palindrome index. So the thing is that if we take a test case SS ABC and there is some other word CBA, so in this context we see that SS is a palindrome, right? So for this prefix index, because of this only the index of that word would be stored in our palindromic index. And then when we uncount, so the thing is that this SSABC, this is a palindrome, right? So because of this, that index would be simply stored in our palindromic index. So that would be the thing. Now comes the part, then we will be able to encounter this particular word, and this particular word was already there in our previous one, right? So because of this purpose only, we will be able to get our answer of the palindrome, because we are checking for prefix and suffix only, right? And because of this prefix and suffix matching only, we are easily able to check that is that particular word a palindrome with other word or not. And in that context only, we would have been missed this case, which makes a palindrome, right? So that's why we are maintaining a different palindromic index vector of vector, where we can easily check for this case that if a partial word is also a palindrome, then is there any other word which makes this other partial word as the palindrome or not? So that's why we are storing in palindromic index. And now the other thing which I have already explained, that we are storing the end of the word index to word matching of the word by itself, right? So this I have already explained. So this was the overview of this trie solution. Now let me show you the coding part of this particular solution, so that you could come up with maybe it becomes much more clear for you. So that's why let us go ahead with that portion. So after checking out the explanation, you can clearly see that this explanation becomes that it is more prone towards the length, right? So that's why here the time complexity is basically order of L square. Why L square? Because we are checking length of each word with other word, because we are going ahead with prefix and suffix. So that's why it becomes L square into N, because how many times we are going ahead with this matching is basically the number of words. So that's why it's L square into N, and the space complexity is basically order of N into L. And this is also somehow completely dependent upon the trie which we are making, because the number of words which are being there and the at max length which could be taken, so according to that only it's N into N. But it could be also, at worst case scenario, it could become N square into L, but that is a worst case scenario which can be reached and cannot be reached. That all depends upon the input of our words. So that's why here the time complexity is this much and space complexity is this much. Now comes the part that how we are required to code this solution. So that's the other thing. Now let us go ahead and code the solution. So here's the coding part. Yeah. So this was a brute force solution which I had explained. Now comes the part for its optimized solution. So here you can see the optimized solution. Yeah, submit. Okay, we can't do more. Okay, let me start from. So here is the struct trie node. So here we are taking three things. One is the root itself, which I've marked as the next, that is trie node start next or 26. Why 26? Because we all know that in English alphabets we are having 26 characters, right? So that's why I've taken as 26, and at the starting initialize with empty string. Next comes the part for int index equals to -1. That I have already explained that how -1. Then next comes the part vector of int palindrome indices, where we are basically storing all the indices for those prefix and suffix which are basically palindrome. So that's the thing. Now here we are basically adding all the nodes which are being there in our trie, and here we are checking for the palindrome, and this is, you can say, the driver code, and here we are basically searching for those words which are being there in our palindrome. Now let us start from this. So here whatever the size of this is, so that taken, and then now here we are calling that add function. That add function is basically for making our trie. So here we are passing the first word, and in this first word we are passing with the index, so that when the word ends, then at that moment only we store that index to the end of the word. And now here when we are adding that, how we are adding that, let us check for that particular moment. So the thing is that first we are directly taking that particular root as a reference. Here we have already taken that, right? So we are taking by reference that particular root, and then here we are going from the reverse side of that particular word, and then we are checking that is palindrome S0J, right? And then what we are doing, we are directly, if at that particular moment or that particular word is having the prefix, which is a palindrome, right? Then we are directly pushing that particular index to our palindromic index vector. So that's the thing which we are doing here. Now comes the next part. Here we are basically making a trie, right? So how we make a trie? We basically check if that particular character or integer already exists or not. If that doesn't exist in a trie, then we make a new node of that trie. So that's the thing which we are doing. Here we are first converting that to integer. And why we are converting that to integer? Because we have taken indices till 26, right? So it comes into the range of 0 to 26 only. That's why we are converting our each character in the range of 0 to 25 by subtracting a from that. So now we are checking that if that particular character exists in a trie or not. If doesn't exist, then we are making a new node out of that by this thing, and then we are moving ahead for connecting with our next node, means for the next time. And then like this, here when this particular for loop ends, means basically now we have added all the words from our, basically all the characters from our word. Then at the end, what we are doing? We are here marking the end of that particular word with I. That is, now our index would be marked as I. Earlier it was at each moment as -1 only. Now here we will be pushing that particular index to a palindromic index. So that's the thing which we will be doing at the end. These all things are just for that fact. When prefix is matching with the palindrome, means basically that prefix is a palindrome, then we are basically pushing those indices at this particular moment. At this particular moment, and if we have already pushed that particular word into our trie, then we are pushing at the end that index. So this is the thing. Now here comes the part checking for the palindrome. This is that common thing only, that how we check for the palindrome. So this is all. Now comes the part that's searching for that word. So how we are searching for that word is, we are now traversing from front to back. Now we will be checking if there is a match or not. So basically, here we are taking our A of I, means that particular word, means that string, and then here we are taking that particular trie. Now we are traversing by taking that particular word. We are traversing that word only. That's the thing which we are doing here. And we are also keeping a check that if that node exists or not. If that exists, then only we'll move ahead, else come out of that. So that's the thing. So here, if that particular node index is not equals to -1, that simply refers to we have reached the end of the word. So in that scenario only, we will next thing which we will check is that index the same as the index at which we are presently. If that is also not the scenario, then we'll check for the next condition, that is that particular whole word a palindrome. If that is, then we'll push that particular into our answer with that index and the index of that particular word which we were traversing till now. So that's the thing which we will be doing here. And now comes the part we will be traversing now our next node. So that's the thing we will be checking here. And then if our node doesn't exist, because then it doesn't exist, then it will come out of here. So if it doesn't exist, then we'll continue. That is, we will be now checking for our next particular, is basically our next word that we will be checking here. And then now here comes the part for the indices which we had stored earlier. So now we will check for each index in a palindrome index. So the thing is that if that I doesn't equal to the j, right, means if it is not the same, then we will be pushing that particular to our answer, and then at the end we will be returning our answer. So this is the whole thing which we will be doing in this solution, and I've already explained the time complexity and space complexity for this particular solution. So this was all for this. Thanks for watching, and if you really like this video, then please do like and subscribe to my channel and do share among your friends. So this was all. Thank you.